Alright, dudes and dudettes, we're on the road and we're gonna go get us some optos. So I should have those in my hands fairly soon. So I'm in my storage unit here, and as you can see by all my mass accumulation of boxed crap, and I thought maybe the things would be in here or perhaps even in here, but they're not. Oh, and before anybody corrects me, yes, I know I screwed this up, so I'm gonna fix it real quick. There's not supposed to be an apostrophe there, so we're just gonna make big S's. Now it says ICS. Oh man. I didn't find them exactly where I was expecting to find them, but this little foam block is actually exactly what I was looking for. I ended up finding it in a box of junk parts that I was actually sorting out. So as you can see, we got a few here, and these are all 817 numbered parts. So we'll take these back down and we're going to see if we can get the projector working. These 817 optocouplers are so easy to find that I already found two right here on these boards. These are just some junk boards in my, obviously, board junk bin. And the one in the center there, that's an 817 numbered part. And this other board right here, this other power supply, also has a couple 817s, these two right there in that spot. Then I have another bin over here of pretty much nothing but switch mode power supplies. And I'm pretty sure I could probably get at least like one of those, like out of each one of these. But this opto right here, right next to this transformer, that's an 817. Those ones down there on the bottom are probably 817s also. So yeah, they're plentiful. And this is why I didn't really want to order any, because I know I got a million of these things. I was wondering where this box went. All right, we're back. These are the optocouplers I brought. What I decided to do is I already kind of went ahead and removed the original optocoupler that was here, which I actually have on the foam right there. And what I also did is I took a 6-pin socket, just like this one, and I removed the two positions that were like on this end, so that way I don't interfere with like any isolation and stuff. And I just kept the two. I would have clipped it, but I figured that was completely unnecessary. And so that way I would just keep the whole thing intact minus the 2 pins right there, since you really only need the 4. And I've also tested it, and did it work? Well, of course we're going to talk about optocouplers first before I spoil the surprise. Gotcha. So the question got asked, how do the optocouplers actually work? Well, they're really simple, and optocoupler, it's an optical coupler. So what we've got is here, we've got just a regular optocoupler, which is a lot like the one that we took out of the projector. And then we have an LED and a phototransistor right here. And this LED, as you can see, they're kind of funky because these actually came from some Christmas lights. And so they kind of have like a cone cut out right in the center. And there's basically something like that, which actually made it cool because then I can sit the phototransistor like right inside of it. There's a little bubble on the phototransistor, like a lens. This right here being an identical phototransistor to the one that I have on there. And then down here on the bottom, I have another LED and another phototransistor. And you might be able to tell that this LED right here is glowing a little bit, but the other two really are not. So the 3 circuits I've got here are like this. This one here basically resembles the same exact thing that we saw in the power supply. So what happens is, when we apply a voltage to the LED end of the optocoupler, the phototransistor acts like as if you've taken the base and you've applied a positive current to it, and it allows current to flow through its emitter and its collector, and then that way it allows the LED that I have here on the breadboard to turn on. Anode side of the LED, it goes through a 180 ohm resistor right here, and I have it hooked up to a battery. It's a 9-volt battery, but it's pretty depleted. So the voltage on it is actually closer to 5 volts, so this 180 ohm resistor actually worked perfect for that. And then the other side is just connected to the negative side of the battery, but I just have it designated as ground here. And then in the second example I have here, I have that blue LED, and that also goes through a 170 ohm resistor. And then this side is going to go to a 5 volt power supply that I've got going on. So basically we're isolating both sides. This side of the circuits is run by a battery. This side is going to be run by a power supply. And then I have the same arrangement on the phototransistor. So these are 2 separate components. There's no physical package linking them together or anything. And then we have the same arrangement here with the LED and the positive supply. And then that's the green LED. And then down at the bottom we have a photo transistor connected to an LED through a 180 ohm resistor to the battery. And as you can see here, I have nothing here, but I will show you why. Alright, so on the left side of this breadboard, this is our 5 volt supply. This is coming directly from a power supply. I've got my positive and my negative here. These two resistors down here, this first one up there is that one. So when I touch that to positive, we can see that the LED lights up, but not because we're applying any sort of voltage or anything directly to this side of the circuit. It's just being optically coupled through the LED inside of that optocoupler and the transistor. All right, so down here in the middle, that's where we have our plain blue LED and our photo transistor. And when we apply a positive to the anode of that LED right there, we can see that well, not only is this blue LED kind of bright, but the green LED lights up as well. And it's, yeah, it's kind of hard to tell right there, but you can see that there's a little bit of green on my finger. So it is lighting up that LED. And again, there is no electrical contact between these two sides. It's just all optical. So then on the last one here, you might be able to see that this LED is glowing a little faintly. Basically, this is the photo transistor right here, and the package itself, if I pull it out, basically looks like a standard TO220 transistor, but it only has 2 leads. And now you can see that the LED actually turned off. So I'm gonna go ahead and put this back in, and you can see that the LED starts glowing as soon as I do so. But if you'll notice, I also have a bit of light going on here. So let me turn off this light, and it's still glowing a little bit. If I kind of block all light, you know, it'll start to go out. You can see it got dimmer there. So here I have a TV remote. If I point it at that photo transistor and I push one of the buttons, it starts flashing. So this is probably the best example of an optocoupling device that you might use in your everyday life. Your remote is obviously, well, yeah, it's a transmitter, and that has the LED on the end, and then your TV or, you know, satellite receiver or whatever else you got would have the photo transistor, and the remote is sending the signals to that photo transistor, and that's how it's coupling the data from this side to the other side. You know, same thing with an optocoupler. You can couple basically like a constant on signal such as this, or you can, you know, like have some sort of like, you know, bit stream going through there, or you can also have like analog signals being controlled optically, because since the other side is a transistor, you know, you can kind of modulate it a bit depending on how much current you're applying to the LED on the other side. So that's basically how optocouplers work. In the case of our circuit in this power supply, what they've avoided doing is actually using a base signal here to control the high voltage side of the power supply, you know, and the LED. So they are just optically coupling the power on signal to the LED, you know, from the control board. This not only electrically isolates the signal, this side of the board and then the other board are not like 100% completely electrically isolated due to the fact that they do share a ground. And then the other board, you know, is powered by the same voltage that's powering the LED. If instead they were just using like a discrete transistor, this base would be electrically coupled to the rest of the control circuit. And if, say for example, that, you know, this were to short this transistor, we would have the full voltage of this power supply, you know, possibly going to through the base pin of this transistor back to the control board, and then it can just, you know, like damage something due to the higher voltage present there, because the voltage controlling it on this side is basically like a really low voltage. So that kind of eliminates that possibility, and it also kind of allows, you know, this power supply to maybe be used with like a lot of different control boards for like different designs or whatever. So all they have to do is apply some sort of a current to this LED when they need the light for the projector to be on. Okay, so the question everyone's asking, did it actually work? Well, let's see. We're gonna hit this power button. I already have the replacement optocoupler in that socket, and the reason I put it in a socket was just to make it easier in case something did happen and I had to, you know, like swap it out. It's not a big deal. It's a little difficult to desolder from this board just because it is kind of thick, so it takes a bit of heat, and I didn't want to like have to, you know, keep like swapping out, just in case one of these optos that I brought also just happened to have something funky going on. So yeah, just to eliminate more headaches, that's why I got the socket. So anyways, here's the power button. LED is plugged in, it got power going to it and everything. So let's hit this button. This is gonna flash a little bit and it's gonna turn solid on. Our fan should start spinning. Fan is spinning. Do we have light? No, it didn't work, much to my disappointment. All right, so what's going on? Well, let's do another little quick test here. So I'm just going to turn this off. So if we take a look at the data sheet for the EL817 optocoupler, it tells us that in the electrical characteristics that the forward voltage of the LED is 1.2 volts at 20 milliamps. So if we take a calculator and we take 5 minus, well, 5 being the voltage that I'm going to be using here. So 5 minus 1.2, that equals 3.8 divided by 0.02 amps. That gives us a resistance of 190 ohms. Well, I don't have 190 ohms resistors on hand, but I do have 180, which should be totally fine. So I've got my 5 volt power supply right here. This is negative, and I got a resistor of 180 ohms on the positive side. So if I take this and I hook up the negative of the supply to the cathode of the optocoupler, and I take the positive and hook it up to the anode of the optocoupler, what happens with the LED on the projector? The power supply is plugged in. So let's see, positive. Oh, it lights. All right, so this works. Let's take off the optocoupler. So this is the replacement optocoupler I used. Let's put the original back in. All right, original optocoupler is reinstalled. Got the same 5 volt supply, negative, positive. Attaching the negative to the cathode side, applying the positive to the anode side. Oh, it works. What gives? All right, so what happened was I sort of jumped the gun. I got a little too excited when I thought that it was the optocoupler. There's been a few power supplies where, you know, I have determined that the optocoupler was bad. So I kind of just jumped to conclusions there and assumed that the optocoupler was bad. I didn't have as much stuff to test on hand back when I was messing with it in the first video. So I did bring down like a few more things with me so that I could, you know, check it more thoroughly. And let me show you something real quick. We saw when we tested it the first time around that we were getting like 1.08 volts or so. But what about the current? Let's check. All right, so here's what we're gonna do. I've pulled one of the leads out of the connector that controls the optocoupler LED side. And what we're gonna do is I've got the meter here hooked up to measure milliamps. I've got this test clip on the positive, and then I've got the black lead here on the common side. So I'm going to clip this to the red wire that comes into the power supply. And what I've already determined by doing a little bit of reverse engineering is that the cathode side of the LED and the optocoupler is actually just grounded. So this is part of the same ground, but the one that actually goes to the anode is the one that's being controlled. So that's why I put the red lead here, because that's the one that goes to the anode. All right, so we toss that to the side. So basically all I have to do is take the black lead and touch it to the anode side of the optocoupler. I'm just gonna kind of move that off to the side a little bit there so you can see it. Okay, so obviously 0 right now, so I'm going to power on the projector. I'm just gonna hit the power button and the fan will spin up. And as we can see, we are getting 1.9 milliamps. All right, so what now? Well, through the magic of reverse engineering, I have determined that the circuit controlling the LED is something like this. The anode side goes to a transistor. It's an NPN transistor. The emitter side of that transistor is connected directly to ground. The collector side is connected directly to the positive. What it looks like they're doing is there is a resistor that goes to a positive power supply, which I have not tested yet, so I don't know what the actual voltage is supposed to be on that. But there's a resistor that goes from the anode of that LED to this positive. So this transistor basically what it's doing is when the unit powers up, this is going to have a it's going to be pulled up to some positive voltage or a positive current, and this transistor is going to be on, and what it's doing is it's basically shorting this LED inside of the optocoupler and basically, you know, keeping this other side off. So when the microcontroller inside of the control board turns this transistor off, that's when the LED gets its positive current and allows it to turn on. So let's check this voltage and see what it's actually measuring. That transistor right there is the one that I drew on the paper. So I can actually measure the voltage at the opposite side of this resistor right here. This is that positive. That resistor right there, which I also have not written down a value for, as you can see here, because I want to know what this voltage is first. That will allow me to determine what this resistor kind of should be to give us about 20 milliamps at that LED. Okay, so we've got the meter set to measure DC voltage. Let's see if there is any voltage present at that resistor there, just as is, without the unit actually being powered up. I mean, we have power applied to the mains, we just don't have the power button, you know, on. So let's see. Aha, so that's 5 volts. Now let's measure that resistor, and as you can see, it's a very tiny resistor. So let's see what kind of resistance value we're getting for that. All right, there's the meter in the shot. I'm going to touch, I already disconnected this from power, so there's no voltage going through there. So let's see what this resistor actually measures. 1.9 kilo ohms. Well, let's just say 2 for the sake of, you know, this thing. All right, so if we take the 2 kilo ohms and we do the math on that, so we'll say, you know, 5 volts minus the 1.2, so that equals the 3.8 divided by 2,000 ohms, 0.0019 amps. So that's 1.9 milliamps. So yeah, I would say that sounds about right. Turns out I really don't have that many resistors here on hand at the moment. Everything's still up there. I kind of should have brought them with me, but I kind of forgot. But fortunately, there is a Fry's Electronics nearby, and I stopped by and picked up this 610 piece pack of E12 series quarter-watt resistors. They're 5%, which should be totally fine. We are going to basically sort of like do a bodge here on the board. I'm not going to go with another surface mount, but it shouldn't be a big deal. The cool thing is that the positive point that I need to tap into is, I think, this one. Yeah, so we're going to put the resistor in line between that point and the collector. How am I going to pick a resistor for this? Well, I mean, obviously I'm not going to pick a 2K resistor, and I just think it's funny that it measures almost exactly 2K. So it almost seems like the 2K is deliberate, but it just doesn't seem like it's gonna give it's gonna drive that optocoupler with enough current. So we're gonna pick something lower, but I also don't want it to be too low that, you know, when this transistor is on and it's basically shorting that resistor to ground, that it's gonna cause a lot of heat to build up. So I'm no actual electronics engineer, I just try to play a mediocre one here on the tubes. But I did a few little calculations, and let me show you what I came up with. First of all, we need to know what that transistor can even handle. So the transistor itself has a marking of 1 AM on it, and if we look that up on an SMB codebook online, we find out that that's an MMBT 3904. So we look up the specs for that. Under thermal characteristics, we see that the lowest number there we have for power dissipation is 310 milliwatts. So we're just going to go with that number. We're just going to go with the lowest number on this. If we were to calculate the power going through a 190 ohm resistor, assuming like no losses through the transistor or anything, so we're just going to go with just the bare 5 volts. So 5, we're going to divide that by 190 ohms, so we're going to get 26 milliamps. All right, so 26 milliamps, I'm gonna say that times 5, then we got about 132 milliwatts, which is, I mean, it's a little bit less than half of what the transistor is rated to be able to dissipate. If we were running that through a tiny, you know, like 0603 or whatever the actual size of this resistor is. It's really tiny. I'm not sure if it is an 0603. It might be smaller. In 0603 it was rated at about 100 milliwatts. So that's a bit of power, you know, going through a resistor like that. And that's kind of why I chose to go with these 1/4 watt ones. But I'm also not going to pick a 190 ohm resistor. I'm going to pick something a little bit higher. But knowing that, you know, we do have a little bit of room to work with there with that transistor, maybe I can pick something in like the 200 ohm range, and hopefully it should still be enough current, because I don't think we need exactly 20 milliamps. We can probably get by with something a little bit lower. And this pack, we have, you know, we have 180, we got 220, 270. Let's try plugging in numbers for a 270 and see what we get. So we got the 5 minus the drop of the diode in there, right? So we got the 3.8. We're going to divide that by 270 ohms, and we have 14.1 milliamps. So now let's see how much heat we're going to be dissipating through that transistor, assuming no loss through it. So 5, once, you know, it's on and it's just shorting that resistor to ground. So 5 divided by 270, we have 18.5 milliamps. Okay, so then we're going to multiply that times 5, and we have about 92.5 milliwatts. So that's not too bad. Okay, so here's my 270 ohm resistor. It's red, violet, and brown. And by the way, if you're wondering what the heck happened to my fingernail here on my thumb, well, it got smashed on the first day we were moving. So it's just been like slowly creeping its way up. The nail's like growing back. So we're going to take the resistor, and I'm going to put it right about there on the board, you know, kind of like in the same location that SMD one's in, except, you know, it's going to be a big 1/4 watt resistor. So let me go ahead and solder that in, and I will be right back. Alright, so there's a resistor soldered in between the 2 points that I mentioned, and I just got it sitting in here, but I haven't plugged anything in yet, so I haven't even tried it to see how it's going to work. But what we're going to do is we're going to reconnect the power supply, and I'm going to take the thermal cam, and we're going to see how warm that area gets just sitting there, because as I said, this thing's basically going to be pumping out a little bit of heat when the projector's not actually on due to the, you know, the way it's designed. But it shouldn't be too much, hopefully. So let's go ahead and connect the power supply, and we'll let it sit there for a while, and we'll see how warm those components are actually getting. Alright, we have it all set up, and I just gotta basically plug it in now. So you can see right there, there's the SD card slot. That other dark spot right there, that's that little crystal that's right next to the SD card slot. So the resistor and the transistor are like right in that area right there. So let's go ahead and plug it in. And sure enough, we see the resistor is warming up, but I kind of expected that. And it seems to be getting a little hotter than I wanted it to. It's already in the 30s there. Alright, maybe that's not going to be a good one. I mean, right now we kind of have a little bit of air kind of blowing through here, so it might not get too hot. I'm just going to let it sit for a minute, and then we'll come back and check on it. Alright, so it seems to have gotten to about 40 or so. It kind of fluctuates a little bit, but then again, like I said, I mean, we have the case open, and there's a little bit of, you know, like air moving through here, so that will obviously cool it down a little bit. But this thing, once it's put back together, is going to be enclosed. So that's going to, you know, that heat's going to build up a little bit, and we kind of don't really want that. But this is going to be the funny part. If we turn this on, I expect the LED for the projector part will actually come on, and this resistor will probably cool off a bit. So let's see if that's true. So I've hit the button there, it should start up. Yep, see? Okay, the LED comes on, just like we expected to. And wow, it's flickering a bit. So yeah, it seems to be cooling off, and I kind of expected that, so alright, maybe let's pick up 500 ohm and see how that does. Alright, so I said 500, but obviously we don't have 500. The closest we have is 470 ohms. So I've got the resistor in place now, and I'm going to apply power. And We can see that it's starting to get warm. And I wish I could kind of focus on that. All right, we're gonna let it sit for a bit and then we'll come back and see what it's peaking at about. Okay, so the temperature is like a little bit lower maybe. Not a whole lot. I mean, but it's also, if like we touch it, it's really not like super hot either. But with this resistor, basically we're looking at about 8 milliamps to that optocoupler. So let's see if it still works. So power is on. And yeah, it still works. So I don't know, maybe we'll just stick with that. I'll let it sit for a while, make sure that it's not getting like way too hot, but I think it should be fine. It just kind of seems like, I don't know, I'm not really a big fan of how they designed that there, where it, you know, shorts out the resistor to ground when it's not on. And now we know that we've got quite a bit of light coming out of this LED because that you can actually feel like the warm air like blowing out of the vents here. I've been letting this sit for a while with just power applied here. You can see how it's a bit warm, like in those areas. Like that's the area where that resistor is, and this section over here, that's calibrating, but that's where the power supply is, and the power supply is always pumping out a little bit of heat because of that linear regulator that it's got built on board. So yeah, it's warm, but I mean it's not like it's cooking or anything. It's just like a little bit warm. You can see right there when I open that up that resistor is a bit warm, but I guess it's gonna have to do for now. I don't know. I'm not totally happy with that, but I mean, it's working a lot better now. I'm not gonna be able to get to focus this close, but you can actually see that, you know, there's quite a bit of light now, so you can actually see it even with the lights on. And if I point this now at the camera, you can see that it's way brighter than it used to be. I was gonna let this thing run here for a few hours just to make sure nothing funky's going on. When I was navigating the menus, I realized that there's a number down here on the bottom right hand of the image, and it says 40N05EN. So I guess apparently this must be a UC40 projector. And I have no idea where else to look for a model number. I just noticed that, looked that up, and yeah, that's apparently the model number. It's a UC40. And then the 05 kind of refers to like the version number of the firmware or something along those lines. I'm not sure, but I think that might be a little more accurate than the UC46 that I thought this thing originally was. Well, that's it working right there. I have it just flashing up on the ceiling. You see if I put my hand in front of the lens, you can obviously see my hand. So it's yeah, obviously way brighter than it used to be, so it is working. I haven't noticed any ill effects after running this it's been running for several hours now, and it still seems fine, so I think it'll be okay. One more thing I wanted to quickly address, and I'm actually recording this after the fact because I don't even have the projector here anymore. I already gave it back. But I got asked why I didn't just short this positive coming into the optocoupler to the transistor side over to like here. Well, that kind of introduces two problems. One is having a positive current over here at this MOSFET powers up the LED, so that would mean that this LED is on all the time if the unit is, you know, plugged into power. The only way we'd be able to get it to turn off is just by unplugging the thing, which would get kind of annoying. And not only that, but the LED would be on, but the rest of the unit wouldn't, so you would still have to hit the power button in order to get it to, you know, like actually turn on. So yeah, that's one thing. And then the other thing is that once you have this optocoupler activated, and if we were to just short the lines over here, is that it also activates the current feedback portion of the power supply circuit that powers the LED. So we noticed that when we had power applied to the power supply, but we didn't have the LED on, that we had a voltage of about 16.7 volts at the output of the main transformer, you know, after it's rectified and filtered and everything. And then we saw that we had about 15.3 going out to the main board. And, you know, this is after the linear regulator. So that's only a voltage of difference of about 1.4 volts. And this, because it is a linear regulator, it's always putting out a little bit of heat. So, but 1.4, you know, is not that big of a difference. So it's, you know, it's still producing heat, it's just not a lot. Well, the problem with having this thing on all the time is that we would have the current regulator portion of the circuit on, And what happens there is that because this is a 20 watt LED that powers the backlight portion of the projector, what's happening is the regulator portion of the power supply wants to keep this LED running at about 20 watts. And at 16.7 volts, we're not going to be able to pump enough current through the LED to run it at 20 watts. So the power supply steps the voltage up to about 21.2 volts, which is that, well, I was a little puzzled, but I mean, it all makes sense now that I think about it. So it steps up the voltage in order to try to get 20 watts out of that LED. And what happens now is that this regulator, trying to keep the voltage regulated at a lower voltage, is now going to have about 5.9 volts difference between, you know, the input to the regulator and the output. So that's going to pump out a considerable more amount of heat. And if the fan isn't running because the rest of the control circuitry is not on, this is going to be getting pretty hot. And the way this unit is designed is that it's got some vents over by the power supply section. So it pulls air in through the power supply, it kind of goes around, it goes through the LCD portion to cool it off. And then it goes out the back where the heat pipes were for that little LED, like the cooling block. So that's why we wouldn't want to have this thing on all the time, because it would just make it annoying where, you know, you would have to unplug it and then you would still have to hit the power button. One thing I didn't notice before, I kind of noticed it after the fact, and I can't show you now, you know, on the board because obviously I don't have it, but it looked like there was a trace that was coming out from somewhere here, you know, that went out. It was right in between the MOSFETs and those current sense resistors. So this here would be going out to the current regulation portion of the circuit. So if this voltage here starts getting too high because there's, you know, too much power going through this LED, then this would kind of lower the voltage a little bit to kind of try to keep the current through this LED, you know, somewhere where it's going to be running at about 20 watts. That's going to do it for this one. Massive improvement. So unless something goes catastrophically wrong with it, it should be fine with just a little bit of modification. And if it does happen to die for whatever reason, then I'm sure we'll see it again soon, since it's going to be getting used. Alright guys, thanks for watching once again, and I'll see you guys around the bench.